Well, thanks for having me here. And as I was telling Steve earlier, I'm going to be delivering a version of this talk to Foundations of Software Engineering in October as a journal first presentation. So this particular talk was built. Let me see if I can find that here. This particular talk was built on an article I wrote last year for redirections in IEEE software. That was with Tim Menzies' column. And we followed up with a blog in January. That blog drew a lot of interest. And apparently this topic of programmer productivity really hit a nerve. But one of the things that I found most interesting was that we had a situation here where there were a number of studies over the years. I think the earliest one in 1968 that replicated that said there was at least a times 10 variation in programmer productivity. And yet, we found evidence that they were all replicating, yet still wrong. This is an extreme version of the replication crisis where they actually do replicate, but they're still wrong. What happened? What did we discover? And here's something where I don't think those of you who have taught personal software process are going to be all that surprised, but we'd never really looked at this quantitatively before. So a little bit of background. Steve, I actually had some online conversations with Steve McConnell, who wrote one of the very good summary articles summarizing the research on the times 10 programmer. Here are some of the citations. And I would recommend for summaries, you go to Steve McConnell's summary that I have cited at the end here. Another good summary is by Robert Glass. But there are a number of different studies. All of them show pretty wide variations in the performance of individual programmers on programming tasks. So what we're going to do is talk a little bit about why does this matter? There have been a lot of suggestions that, well, this is really an important thing to know because it means you really should be hiring the best programmers, that the best programmers are the ones who are going to drive your success, that you should worry most about. In fact, you probably should pay them the best. But what about things like education, training? What makes a good programmer? What makes one programmer better than another? How do you find the best programmer? How do you identify them? How do you evaluate and promote the best programmers? What does this have to do for planning, and how do you retain them? So these were the questions that were in my mind when I started looking at the data. So the questions were, do we also replicate this times 10 performance difference? And secondly, I wanted to look at what factors. Was it education? Was it experience? Was it something they were doing with the work, for example, design, that made the difference? And I wanted to not only explain the difference, I wanted to find a causation. What caused the difference among these different programmers? I won't go into the details right now, but we've been working on a program called Scope at the SCI. It's just wrapping up now, where we're using some modern tools developed by Judea Pearl and developed at the Carnegie Mellon Institute with Carnegie Mellon through the philosophy department of all places, where you can use mathematical techniques to actually infer causation. We all know correlation is not causation. But if you use the right graphical techniques and you have the right circumstances in how the graph is constructed, you can infer the direction of causation between two factors. So I wanted to try to apply this and figure out what were the relationships and what was causing the effectiveness of certain programmers. Now, fortunately, I have a pretty big data set. These are all based on the original PSP. Many of you are familiar with this. Some of you probably taught this version of the course. It was 10 programs. These are the programs that come in Watt's thick book, the blue and orange book. 10 exercises. Everyone did the same exercises. Well, mostly a few did the B exercises, but you know the A exercises 1 through 10. The only variation was partway through, we took the cyclic development and kind of said, well, that really isn't necessary. We're just going to stop at PSP 2.1. Turns out that doesn't make much difference. It's still the same exercises. And I won't go into a whole lot of detail on PSP here, but because you all know that we measure the effort, the defects, we break it into activities and phases to find the workflows. This gives you a lot of insight into what's going on. But what I'm really interested in for this study is the effort. How long did it take them to do this task? And what were the factors that drove the differences? So what did I do? I took the PSP data. But focused on effort as my outcome. How long did it take? I wasn't looking at things like, I wasn't initially looking at things like, well, how much effort did they put into different tasks, different subtasks like design and testing or reviews. I did look at the individual programmer ID, so I separated them by programmer, and I separated out the individual assignments. So what I did was each assignment had some class average time. So I used that for each individual assignment as the benchmark. Instead of measuring the size of the programs, I said each program took some average amount of effort. I'm going to norm each group by the program assignment. Okay, so what was the programmer's relative effort within that group? I limited this particular study to just C programmers. We have some big samples on Java, Visual Basic, some C#, but the biggest single sample was C programmers, and for the best apples to apples, I wanted to avoid confounders. So for this one, just C programmers. Every program written here was done in the program language C. Yeah, I scaled the effort by the program. Then I looked at the individual factors. Now, what are the things that you would think would make a difference? Well, we have things like design time. How much effort did you put into design? Did you do reviews? How much difference did those make in the total effort? And spoiler alert for those of you who have done PSP before, we always found the productivity never really varied much during the course of the PSP. Remember the average productivities were the same at the beginning and end of the course? Well, oddly enough, that data replicated here, and none of these factors were driving a productivity difference within or between developers. So it's like I was getting a null result. There was nothing that indicated that predicted the programmer productivity. And oddly enough, even the programmer ID wasn't a very strong predictor. Well, what was going on here? There were no good correlations. Nothing correlated with anything. But what I would call the within variation was surprisingly strong. Now, those of you who have taught PSP know that we always presented data to the class. And we would typically show these data in terms of quartiles. It was completely unattributed, but people could look at the data and they knew where they fit in. And what did we always tell them? Don't worry if you weren't one of the top performers because you're going to move around. You're not going to be, mostly it's not going to be the same people, the top or bottom performers on each program. And that was one of the things that we always told people, but we had never quantified it. I'm going to show you some quantified data that shows that not only does that performance from the individual vary, but it varies a lot, and it varies so much that it makes a huge difference in how you analyze this data. I also did some linear mixed models. It's a mathematical technique that I don't want to go into a whole lot, but that showed that the individual programmer results were they were about as variable as the between programmers. That means that if you knew who the individual was, you could get about half the variation in productivity, but only about half. The rest of that variation was the programmer's variance from one day to the next. So I thought I'd look at this a little more carefully. The first thing I did was I took the total effort in the course. So for those 494 programmers who programmed in C, I summed up the total effort and then divided the total effort by the total average. And the x-axis here is basically in percent. So if you can see the peak here, is a little over 60%. Well, what that means is that the peak or the median of this, the median here was actually about 80%. The average was at about 60%. That means that you've got a very skewed distribution. Okay, the distribution has a lot of outliers on the long side. The average programmer, the median programmer, took about 86% of the average time. Now, 25%, the first quartile took about 63% of the average. So the top quarter performers were about a little over 60% of the average time. So they were pretty fast. The third quartile, up around here, were only at about 25% above the average. And it wasn't until you got to the 95th percentile that you got about twice the average. Now I'm looking at this and I'm saying something still doesn't look quite right. 95% of the 95% of the sample is only twice the average time. That doesn't sound like 10 to 1. Well, to get to 10 to 1, you have to start looking at some of these outliers. And there are literally a couple of outliers who took too long. This is sort of like the example of the person who decided to write a regressive descending parser for assignment 2. If you remember assignment 2, the line counter. That's where we told them you should just be doing the simplest thing possible. But if you try to actually parse the code and write a sophisticated line counter, you can turn this into a much more difficult problem. And that's the sort of thing we're seeing here. Or people who just got stuck on a hard problem and had a really hard debugging issue. Most of the sample were within a very narrow range. In fact, only 5% of the programmers were more than twice as fast as average. So basically you have 90% of the sample within a factor of 2, plus or minus a factor of 2 of the average. It's not as big a difference as it seems like. Okay, let's dig a little bit more. Quartile chart. I did the quartiles on performance, again, normed to the individual exercise. So this is basically normalized to 1.0. 1 is the average performance. And these are the quartiles of performance times for the different programs. And what's kind of striking here is, wow, those quartiles are almost identical from program 1 to program 10. You have pretty much the same amount of time in the distribution, about the same number of programmers, were right around the median every time. I should say about the median program time was about the same for each of the programs. The same with the first quartile. The first quartile was typically in a pretty narrow range between half as fast and 60%. And the third quartile, well, they were typically about 25% longer than the average. And that was rock solid. Where you get a lot of variation is the maximum. So a lot of variation at the extremes. There was always some straggler, right? Someone in the class always had a problem and got stuck. And that variation on the straggler is one of the things that is really kind of striking. But there's something even more interesting. The straggler was certainly not the same person from time to time. In fact, although these charts seem to show the same amount of time by quartile, those are not the same people in each quartile. And I thought about how to display this, and this is what I came up with. For each individual, you see there are 494 points on this chart. And I ranked them by their average. What was their median? What was the individual's median rank? So you sort the percentage time for an assignment, you rank them 1 through 149. What was the middle rank for each person? Then I took, well, not the extremes. Let's not look at the extremes. Let's throw out the top 2 and the bottom 2. And what that tells you is this is a non-parametric estimate of their rank range. What is their true range? If I can throw out the top 2 and the bottom 2, I can say somewhere within that range is going to be a 90% confidence interval on their true ranking. So if I were to show the entire range, this chart would show wider bars. So essentially, let me back up a second. If I take one of these, whoop, I didn't mean to do that, sorry. Where did that go? There. If I take one of these bars, this individual finished, finished in this extreme at about 350, ranked 350, and here this individual finished at around 80. So this individual, 90% of the time, was going to be somewhere between 80th ranked of the group and 350th ranked. What does that mean? It means that over 10 exercises, the best you can do is say this person is somewhere within about 2 quartiles. That's all you could say because their variation was so wide. And if you look at these variations, they give you kind of a hint on how hard it is to distinguish one programmer from another. Now, if I go to the extremes, the top 5% of the programmers, well, the top few percent of the programmers consistently finished within a quartile, within between 1 and 100. But that's all I could say about them. Think about that. The best I could say about the best programmers was they consistently were in the top 20%. Similarly, there were a few stragglers out here, but once you get beyond the last couple, the most I can say is they consistently were finishing somewhere in the between the worst 20% and maybe the worst 40%. This is a pretty big range. In fact, most of these extended over a range. The average width between the top and bottom was 250 out of a sample of 500 in round numbers. Think about that for a minute. We did 10 exercises. We measured their total time 10 different times. And the best we could do is rank them within about half the sample. That's kind of a sobering thought. Now, what does this mean? This is actually an interesting observation because it tells us that what we have here is a huge within programmer variation. In the social sciences, you often see a distinction between within and between groups. Within group basically tells you how much does the group information provide you. In this case, the group is the individual. How much does knowing the individual tell you about the productivity? And in this case, it tells us, well, if I know who the programmer was, that only gets me about half the total variation, very roughly. An implication of this is that when we look at these historic studies, they were mostly point studies. That is, they did a single measurement. They had a bunch of programmers do the same exercise and then said, oh, look at the range between the programmer performance. This is at least 10 to 1. And looking at this data, I'd say, no, you're misinterpreting that, because at least half the variation you've measured there is actually just the noise of the individual programmer's performance. Huge variation in the individual performance, so you have way overestimated the difference between programmers based on point values. And this had escaped notice for 50 years. As near as I can tell, this is the first time anyone has ever quantifiably demonstrated this effect. And most of you who've taught the course kind of intuitively knew there was something like this going on, but I was kind of surprised myself at the scale of this. So the real difference between the best and the average programmer is really pretty small. It's really pretty modest. It's not tiny, but it's about 50%, and about 50% between the middling programmer and, say, the 95th percentile. So they've got maybe a factor of 4 would be a reasonable range. And yes, if you count the straggler, you might be able to get higher ranges, but you're really not capturing a meaningful number. Most of the programmers really perform within a fairly narrow productivity range. Now, an observation about this, it exaggerates the previous work had exaggerated the actual ranges by conflating the within and between, and even with 10 exercises, I can't place programmers more narrowly than within 50% of the sample. And that has some implications. But let's talk about a few of the limitations of the study before we talk about the implications. First of all, I only use C programmers. We have other samples. It would be nice to follow up with this and see, does this replicate with Java, with C#? Cursory samples indicate, yeah, this pretty much does hold up, but it would be nice to look at it more carefully. And I can also look at this with some more sophisticated mathematical and numeric approaches, like the linear mixed models, which I'll discuss very briefly. What else could there be? Dropout bias. Everyone knows that there was a dropout. There were dropouts along the course. We're only measuring the people who actually finished. So that's going to tend to compress the range. What I found, though, was that the dropout bias, when I looked at this, didn't really seem to be affecting my numbers that much. That doesn't seem to be a big effect for me. There certainly is a potential for selection bias. We only measured people who came into this course in the first place. But again, these were mostly industrial courses, so these were largely not self-selected. These were selected by the companies, so that kind of mitigates the effect. Some of the programs had a lot of reuse. So there might have been a reuse component that I didn't measure here. And there might be other significant differences that I just haven't really accounted for. With those caveats, what does this mean for industry? Well, my first caution would be you should really think twice before you rank your programmers, because you probably don't have enough data to make a real judgment. Based on 1 or 2 points, the best you can do is narrow them down by about half the well, even after 10 points, the best you could do is get them down to about 50% of the population. With 1 data point, you have almost nothing. And in the real world, you don't have comparisons of people doing the same work. So I think that's a real problem. I would recommend, if you're in the industry, you really need to focus on basic competence. Can people competently do the tasks that you're asking them to? And don't try to chase the unicorn super developer and think that it's going to greatly improve your overall productivity. I mean, it's not that there aren't pretty good programmers out there and they can't solve really hard problems, but for most of your day-to-day programming, there aren't enough of them to move the dial. Do be aware and don't overreact to variation. There's going to be a lot of variation from programmers from day to day. And it's not just because they're having a good day or a bad day, or it's because they're working on a problem that they're familiar with or not familiar with. There's just lots of things that potentially can cause these variations, and it'd be nice to understand that better. But right now, all we know is it's a major effect. Let's see. I would focus more on creating good work environments. Create good work environments, good work habits. One of the things that always drives me crazy is doing things like irregular hours because of mandatory work meetings and the like. You want some consistency. You want to be able to think about how to provide people good training, how to get peer helps, recognize outliers for interventions, and so forth. But it's work on creating good work environments rather than trying to chase after unicorns. For researchers, there's a really interesting problem here. We had something that escaped attention for 50 years. How does something like that happen? I think part of it is you really have to think hard and document your assumptions before anything else. What we have here is a fundamental problem where we did not consider some of the validity aspects of the data. The first and most important was reliability. Reliability is how predictive is a particular measurement. In this case, a measurement of a programmer productivity doesn't really tell you much about the productivity on the next assignment. If you get about 10 of them, you can get a narrower range, but you need a lot of data to get the prediction. It's just highly variable. Again, what are you trying to measure? We focused a lot on productivity. All of these measures were on things like productivity measures. What did they really tell you? Well, when you looked at things like min-max, all they told you was things like, how long is someone willing to work on this problem before they give up and drop out of the study? And that answer seems to be on average somewhere around 10 to 1, because that's kind of what we were seeing in the final analysis. But it doesn't really tell you much about the real range of productivities. What are you measuring? What are you trying to measure? What are the conditions, and so forth? From a research standpoint, I think we really need to put a lot more effort into measuring environmental factors that'll help programmers become more effective, more consistent, and more productive. And if you want to look at the PSP data, I have placed the data anonymized on the IEEE data port, along with some field descriptions. What can we look at in the future? Well, this particular chart shows what is called the intraclass correlation. An intraclass correlation of 1. That is, if I measured a value of 1, it would say knowing the individual tells me everything I need to know, and all the variation is between them. That is, if an ICC, an intraclass correlation, is 1, you would get perfect prediction for the individual with a measurement point. If the ICC is 0, then knowing the individual doesn't tell you anything. Then it doesn't matter who the individual is. All the variation shows up elsewhere. What I found was for the relative effort, the intraclass correlation was measured about 0.6, a little over half. If I looked at this in terms of production rate, lines of code per hour, that was about 50-50. Defect density even less. So what it tells you, and then I get down to the estimates. By the time they were trying to estimate code, knowing who was making the estimate provided me almost no information about the result. So what that tells me is the relative effort actually was the most useful, the most reliable of these quantities that I measured for individuals. And that's also kind of sobering. All of these other factors are increasingly less relevant as you get down to the individual values. I'd also like to take a deeper look at these with comparative programming languages. We're doing a look at that with a study with one of Tim Menzies' students. So I hope we can see that published pretty soon. So let me give you a quick summary. The scale of individual variation has been under our noses for 50 years, and no one noticed it before. The obvious question is why, and I think the answer is because no one had any data on this. It's a hard thing to measure. To measure this, you need to measure the same person multiple times, and you need to compare them to a group of people doing similar tasks. Measuring productivity is hard. This particular data set is really unique, and I really recommend it to anyone who wants a tool for training machine learning, or a tool for teaching students. But it's really interesting to see what we could extract from this after all these years. No one had previously thought to quantify the reliability of the measure, probably because they couldn't do repeated measures. It's really hard to get people to do multiple programs and measure all of them. Predictive value across what units? You really need to think about these sorts of things, and what are you trying to measure? So one of my biggest takeaway from this is, what else have we missed? If something like this could be right under our nose for all this time, what else are we simply not noticing, probably because of our preconceived biases? If you have some ideas, I'd love to take a look at them and have you share your thoughts. And acknowledgements. I want to thank the PSP team, who not only developed the classes, but took most of the data here, along with the anonymous anonymous instructors and people who took all of these courses and shared the data. Tim Menzies put a lot of effort in helping me develop this article for IEEE. And here is a picture from the time we went to Disneyland. And I grafted Watts. Watts wasn't with us on that day, but this was my favorite picture. And every one of you probably remembers Watts. And with that, here are some links to the IEEE article and the PSP data. If you have some questions, here are some references. If you have some questions I would like to discuss, I'm all ears. This usually generates quite a bit of discussion.
So actually, Bill, this is Alan. It was Watts in the Mickey Mouse suit. We didn't know that.
So if you have questions, feel free to unmute and ask your questions, or feel free to put them in the chat. Bill, how much space does that data set take on your computer?
I'd have to check. It's in a single spreadsheet. It's not really huge. It's got, what, a couple hundred columns, but it's about 4,000 rows, about 5,000 rows. I'll give you a measure later on the actual size. It's not.
That's fine. I'm willing to download it then.
Yeah, it's not as big as you might think. It's probably a couple of megabytes, but it's not huge.
Okay.
But that particular data set was anonymized. I took that out of the Access database, turned it into a single table on a spreadsheet.
So a question is, Bill, do you have similar analysis from industry programs?
By industry programs, I'd like some clarification. But by industry programs, do you mean like the TSP data with productivity?
Yeah, I would think that's what it's meant.
Okay. Yes. And the answer is you can't do something quite like this with industry because what makes the PSP data unique is everyone programmed to the same specifications. So I could certainly do other types of analysis. I could do analysis based on things like line of code, but the line of code counting in industry is a lot less reliable. We had a lot more control in the PSP data. In principle, we can do some similar types of studies, but there are going to be differences, and those are worth discussing.
Right, because while there will be limitations, there's still implications.
There are still implications, and you can't do the apples to apples study in industry, and that's part of the message here. This is the best I could do with the most tightly controlled data available. If I give you something from industry, the error bars are going to go up because it's simply going to be harder to control these confounding factors. I won't be able to control the type of problem they're working on. I don't necessarily have the information on the programming language they were using. We don't have as much constraint on how accurate on the defect levels they were willing to tolerate and so forth, how many test cases they ran.
Yes.
A lot of noise.
Question. In the last year or so, I've consumed like as many books as I could to understand the programming and coding world, and one of them was this one, Coders. I don't know if folks can see that on the screen, but there's anecdotes, lovely anecdotes about these formidable superstars, right? The person that stayed up through the night. How do you explain away those anecdotes, right? And do you think that your data will penetrate the population of believers that the 10x coders exist? Like, while it seems like your data is showing that particular problem they were solving and that particular energy that they had at that moment and that particular passion that they brought to it, and yes, they were a high performer, but given the long arc of their career, like, there probably isn't as much variance, and these are just mythical stories. I wonder if you could just kind of talk about the comparison between your findings in the data and then the anecdotes in the world?
Yeah, that's a really interesting question because it really comes to the issue of construct validity. What are you actually measuring? We were very narrowly measuring the productivity on a set of programs that were of a fairly limited range of complexity, a fairly limited range of difficulty, and a fairly limited scale. But that's more or less what all of these other studies were measuring as well. So I think the first thing I would do is be cautious about reasoning from anecdotes. That anecdotes can be entertaining, they can be a start of something, but you see a lot of this in sports statistics too. There's been an ongoing debate in baseball about the clutch hitter, about the hitter who is great in the clutch, and what that usually means is he got a big hit in an important situation where there were lots of sports writers around. And that's how we fool ourselves. You probably, if you, I think you may have read. There's a whole book called "Fooled by Randomness." So I think there really are truly exceptional programmers, just like there are truly exceptional people, those with the 160 IQ who win a Nobel Prize, but they are extraordinarily rare. By and large, I think what my data suggests is for the ordinary types of applications that we're running, if you're going to see a lot of variation day by day, and if you actually had data on the long run, then you would see that there is a fairly narrow range in performance between the best few percent. Let's just cut that off at 5-10%, and the worst 10% of people who are competent enough to keep their job. Even that, it's going to be a significant difference, but it might be a factor of 4. Yeah, most of that times 10 is in fact driven by who was the last one who actually got a measurable data point. It's measuring how long they were willing to put in before they gave up. So yeah, there are going to be some super programmers. I think someone like Linus Torvalds would qualify, but the data suggests that if you're trying to make a productive team, you're not going to get very far trying to find a bunch of Linus Torvalds because there just aren't too many. Right. And even then, they aren't going to move the dial on your team productivity all that much unless they're solving some super hard problem that no one else can.
So your research acknowledges that there are these mutant outliers that are immortal or whatever, and they're just very special. And then when managing like the real population of coders, either in an industrial setting or an academic setting, it's important to know that the data doesn't support a 10x coder perspective.
Well, let me just acknowledge that it's perfectly plausible that there are these unicorns out there. And personally, I think there are, but I don't have any evidence of them, other than things like the existence of someone like Linus Torvalds. But yeah, for the day-to-day programmer in industry, you're going to get what you can get. And trying to hire a super programmer just doesn't look like a productive way to spend your time. I think you could make a lot more progress trying to build solid teams and build good work environments.
Bill, the bigger problem is that most programmers think that they're above average.
Well, yeah, and
hey, Bill. I mean,
well, here's the funny thing. Let me go back. Let me find my chart here.
They all think they're top quartile.
Here's the funny thing.
Data.
Most programmers are above average.
At some point.
Here's the data that proves it. What is the median is at 86%. The mean is at 1. That means that more than half the programmers are faster than average. You can't make this stuff up.
Bill, this is Steve. I was just curious, what kind of time frame was this data collected in? I assume probably from somewhere in the mid-90s to maybe the 5 years ago or something like that?
Okay, this is actually a little bit older than that because, as many of you might recall, we made a significant shift in the course in 2006. So this data, the last data point on this is from about 2006, after which we moved to an 8-course exercise, an 8-exercise course.
Right.
And I didn't want to, and they were different problems. And also at that point, that's when we started having a lot more student involvement. This data is dominated by people from industry. If we move to post 2006, a lot of the data is going to be coming from people taking courses academically. And I didn't want to conflate those. I didn't want to look at different courses. You could actually do some similar studies with data from the 8-exercise course or even the 7. But someone's going to have to dig that out of the access databases, the individual access databases, and that's going to be a lot of work that I haven't gone to.
So roughly 1994 to 2006, something like that. Thank you.
That's about right, yeah. Oh, and by the way, one of the things we found was that experience had almost no effect on productivity. To the extent that there was experience, there looked like the more experience tended to be a very slightly negative effect on productivity. I have no idea what that means, except it might be that I could make some guesses, but it could be a dropout bias of the best programmers getting promoted into management and not taking part in the course. It might be less familiarity with the newer techniques that were a bit more productive. No idea. It was such a small effect, though, that it didn't really matter. And there were no effects on things like education, no noticeable effects on amount of experience with the programming language or the number of lines written. It's nothing correlated. Absolutely nothing.
Hey, Bill, this is Brad Hodgins.
Hi, Brad.
I got a little piece of data for you on the unicorns. I learned about TSP in 2000, so ever since about 2005, I've been involved in coaching. So about 15 years of coaching. I have on my teams less than a handful that were 5 times or better than the rest of the team members and sustained it. That's in the TSP environment. So very rare animals, but they exist. I can probably mention 3 by name, but definitely less than a handful in 15 years.
Yeah, and you know, if you're talking about a factor of 5, that's actually getting into the range of something that's plausible. You can see in our data we have, in the PSP data, about 5% were twice as fast as the average. And that number goes down as you get to smaller nodes, but if you get someone, there probably are a handful that are 4, maybe even 5 times faster than average, but they're going to be very rare. And good luck trying to find them and keep them.
Okay, I just want to make sure we have a little bit of time left at the end of the meeting today to go over some C business. Are there any other questions? And you know, feel free to reach out to Bill privately as well.
And if you have any comments, if you have any comments, please send them on, because I do have to do this one again for Foundations of Software Engineering.
Okay, I have a question, maybe just an opinion. I would like to mention to you, William. I am very surprised by your research. If we acknowledge that, I'm sorry, Francisco Valdez from Mexico. If we acknowledge that maybe the variation for the programmers in the specific work of the software development, considering the very small, very controlled environment of the developments in the course of in the PSP teaching course, which indeed is very interesting. This acknowledge lead us that maybe the huge variation of huge rate of failure projects in software are more related to other elements or to other, let me say, like this, in the other steps in the software development process. I mean, not in the construction indeed. I think an interest issue could be to measure the productivity in the other steps. I mean, maybe the huge variation are not in the development indeed, but maybe in the skills for the people to get the good requirements, or maybe to make the analysis, to define the architecture, maybe the testing, so on. So the problem that I see there is that maybe we cannot use the line of code. So maybe we can need to compare this research that you made, that is very interesting, as I mentioned, using some other comparable unit that allows to compare the productivity in the construction step or phase with the analysis, with the requirement phases, because maybe the huge variation, as I mentioned, are not in the development, maybe in the other areas that I think could be interesting for the industry in order to generate several elements like courses or improvement the skills for the people related in that areas, for example, business analysts. I don't know what you think about it.
I think it's a very good comment. I'll probably make some adjustments to the recommendation slide to make sure I include not just environments, but other aspects of software engineering. The development itself is probably, the coding itself is probably not the big source of variation and issues on software projects. I mean, it certainly could be, but the evidence here is that there's something else going on.
Yeah.
And it would be nice to know what it is so we can do something about it.
Okay, so in the interest of time, I'm going to cut off the questions for now. But I want to thank Bill for his wonderful presentation and for going through all that analysis of all that data. I want to encourage people to download that data and do similar or extend the analysis. It's all interesting data out there. So join me in thanking Bill.
Thank you.
Thanks, Bill.